Hey, Tim, come, we're getting ready for you. Hey, what happened to your face?
I have a date tonight with Blackpink Jenny, and my face, I'm having an acne breakout.
Oh no, but don't worry, I can see you're putting acne cream. Now, acne cream contains salicylic acid, and they will react things away for you. So don't worry, you'll be fine, right? When the pimples go away, your worries go away too.
I don't know. I think that's a bit dodgy, mate.
Wait a minute.
Mr. William, it worked. My pimples, they're all gone.
Yes.
Yeah.
How was your date?
It was fantastic, man. It was a great evening.
That's great. Trust the process.
So, Mr. William, can you tell me more, right? So, how did the carboxylic acid actually react with the pimples on my face?
Well, to understand the reactions of carboxylic acid, the first thing we must know is the chemical properties of carboxylic acid.
Okay.
All right. So where do we go to? We go into our encyclopedia. All right. So let's go. Now, if you look at the carboxylic acid, now as always, the very first question we ask is, are we looking at nucleophiles or are we looking at electrophiles? Right. So the focus right now is on this carbon. As you can see, the carbon is bonded to two highly electron-withdrawing atoms, which is oxygen. And what the oxygen is going to do is going to withdraw electrons from those carbon, right? And the carbon is therefore going to be electron-deficient. The carbon is going to have a delta plus. So the chemistry of carboxylic acid is to always learn that they are electrophiles in nature. If they are electrophiles, you do expect nucleophiles to be able to attack them. So the primary focus, carboxylic acids are electrophiles.
Okay. So, of course, like what Mr. Williams said, if they're electrophiles, then nucleophiles will attack them, all right? Now, I'm going to show you a very simple mechanism first, and it just looks like this, all right? I'll draw this here. So, we have a carboxylic acid molecule here. So, tell yourself that carbon there, that we just talked about, is electrophilic, which means if a nucleophile comes in, it's going to attack the electrophilic carbon, it kicks out that OH, and you get this, okay? Now, but here's the thing. Notice this with me, right? You can see how the nucleophile has just substituted away the OH in this final product. So this is known as your substitution reaction. But here's the thing, Mr. William. You can see an OH minus that just left the molecule.
Yep.
Now, is OH minus a stable molecule?
No, it's not stable because it's charged.
Yes, again, right? Charged molecules are not stable. So in other words, this mechanism is a little bit wrong, all right? So to make your OH minus into a better leaving group, we don't want it to leave with a negative charge. We want it to leave as a neutral molecule instead. So how do we do that? We use H+, okay? So what's going to happen is this. Now, this mechanism here is way too complex. It's like almost H3 level, so I'll dumb it down even further, okay? So I'm going to draw for you a carboxylic acid molecule here. Now, Mr. William, I'm going to expose this to H+. Now, our end goal is to convert this into water, right? So how do I do that?
Well, you could use the lone pair on the oxygen,
right?
And the lone pair on the oxygen, you can see it like a dative bond towards the empty orbital of H+. So you're going through the protonation process.
Ah, so it's like an acid-base reaction then.
That's right.
Okay, so it undergoes an acid-base reaction. The carboxylic acid accepts the H+, okay? And you see this here, all right? So now when the nucleophile comes in right now, and it attacks that carbon, okay, and kicks out the OH2+, it will not leave as OH minus anymore, it will leave as water. And water is way more stable than your OH minus that you saw just now, right? That's it, okay? So this is again a very simplified mechanism that is going to help you to understand further reactions. So long story short, let me wrap this up. Carboxylic acids, they undergo nucleophilic substitution, but take note, this substitution is happening on a carbon that is part of your acyl group. So it's called nucleophilic acyl substitution, okay? Let's go.
Now, if you look at your reactions, if you look at the mind map, there are several reactions that carboxylic acids can do, but some of them, they are quite similar. For example, if you look at reaction 10.1a, b, and c, you do notice that the products are the same, right? You do notice that the carboxylic acid is changing into the corresponding carboxylate salt, and that can be done using several reagents. Now, we can use either sodium hydroxide, or sodium carbonate. They are similar with subtle differences. So why not we bring out the differences to the students? All right, so let's go down a little bit. Now, if you look at reaction 10.1a, it's a reaction with sodium. Now, the reaction with sodium is not an acid-base reaction, right? Rather, we're going to call this a redox reaction or an acid-metal reaction. Now, why is this a redox, Mr. Tim?
Well, because the sodium is actually being oxidized, right? while the carboxylic acid is actually being reduced into H2 gas. Okay?
Yes, all right. So this is a redox reaction, and the end result is going to form hydrogen gas. Now, one thing to be mindful of is really the mole ratio between the carboxylic acid and hydrogen. So you do notice when they react together, 1 mole of carboxylic acid actually produces half mole of hydrogen gas, not 1 mole of hydrogen gas. All right, that's 10.1a. Now, if you look at 10.1b on the next page, now this is a classical acid-base reaction. Right, so you can see this is just an acid reacting with a base. So every time acids and base reacts, what do they form?
Salt and water.
Exactly,
Yeah.
right? So you have here salt as well as water, okay? And if you look at 10.1c, slightly below, you will notice it's a reaction with carbonates. Now, carbonates are known to be a weaker base as compared to NaOH, right? But this will be termed as an acid plus a carbonate reaction. So acid plus carbonate is always going to form.
Salt, CO2 and water.
All right, that's right. So you're
Yeah.
going to form carbon dioxide as well as the salt, right? So you do notice this reaction is actually what we call a distinguishing test. So whenever you suspect something to be a carboxylic acid, just put it in carbonate and you check whether CO2 gas is being produced or not. And how do we do that?
Well, you bubble it through lime water, right, or calcium hydroxide. If you see a white PPT forming, then you know that CO2 gas is present.
Yep, that's
Okay.
right. So these are the 3 reactions whereby you can form the salt 10.1a to 10.1c. Just realize that 10.1c has extra significance because it's a distinguishing test for carboxylic acid.
Alright, students, so reaction 10.2, again another reaction of carboxylic acids. Now we have seen this before in hydroxyl compounds. So just to remind you, carboxylic acids, first things first, can react with alcohols to give you an ester, right? Your C double bond O functional group, alright? Now, we're going to do it the simplified way. So come students, draw out this alcohol with me, OH, bonded to this R prime, okay? We're going to do some circling, alright? So circle this with me, circle the OH in the carboxylic acid functional group, circle the H, now that's water, remove it, get rid of the water, and you can see water being produced here, and whatever you have left, so let me just do this with you, delete off, I'll bring this, and I'll combine in, like, oops, and I'll combine in. Now you can see what I've just done. I've just created this ester functional group that we have here, okay? Now, there are a few things that you need to remember, if you guys forgot. Now, this reaction, it is reversible, okay? Now, Mr. Willem, if it's reversible, do you think my yield will be high or low?
Reversible means you have a low yield.
Yeah,
and
now
that's
it's a
always
low
a
yield.
problem.
Yeah, it is, right? So, Mr. Willem, help me out. If I want to push my puree to the right to increase my yield, how do I do that?
One of the ways is by using Le Chatelier's. As
Okay.
you can see from the equation, water is being produced. Therefore, if we can find a way to remove water, naturally by LCP, the equilibrium is going to shift towards the right-hand side. And guys, bear in mind, H2SO4 concentrated is always a dehydrating agent.
Okay, yes. So exactly what Mr. Williams said, corn H2SO4 is a dehydrating agent. You get rid of the water, the puree pushes to the right, and this increases the yield of your ester. Okay?
Yep.
And that's it. And guys, this mechanism here, we won't do it here because it's a bit more complicated. We'll do this in class with your teachers. Alright?
Alright guys, now let's take a look at reaction 10.3. Now 10.3, I think we're not going to go into the mechanism, but we're going to look at before and after. The idea is to change carboxylic acid into this substance called acyl chloride. Now you can see the OH is going to change into the corresponding chlorine, and there are several reagents to do this, which is very similar to what we learned in hydroxyl compounds. We have PCl3, PCl5, and SOCl2. Now what is important is to note the side products of the reactions as well. So for example, if you're using PCl5, then be mindful, POCl3, HCl are the side products. SOCl2, we always say this is like the preferred reaction to do this, and what is the reason for that, Mr. Tim?
Now, if you look at your byproducts, yeah, SO2 and HCl, they are gaseous state. Yeah?
Right, so if they are gaseous, then it becomes a lot easier for us to remove from the product, which usually is going to be a liquid. All you do is you hit it, all the gases, they're going to disappear, and there you have all the products. We term this as a cleaner reaction, right? If you compare this with PCl5, for example, notice your product is a liquid. POCl3 is also a liquid, right? It's going to give a problem because they're going to mix together and separation is going to be a lot more tedious, right? So just be mindful, as OCl2 slightly below, this is going to be the preferred reagent.
Okay, so like what Mr. Williams said, we have actually seen this in hydroxyl compounds. So in reaction 7.3, was quite simple, right? So same thing. The only main differences here is that instead of the three reactions that we just saw just now, we also have the first one that reacts with HCl. So an alcohol reacting with HCl to give you your Rx. Okay. The rest of them here, again, they're all the same, so I won't run through this with you. Just take note, this is a preferred one for the cleaner reaction. Okay.
So it kind of allows students to be selective in their reaction,
Yeah.
right? So let's say you have both functional groups present and you only want to react the alcohol away, then the only choice of reagent you have is going to be HCl,
Yes.
right? Because the other reagents, they are not going to be selective. You're going to react with both of them away, right?
Alright.
So be mindful, selective reaction.
Alright guys, so in reaction 10.4, what we have here is the reduction of a carboxylic acid. So carboxylic acid becomes a primary alcohol, take note, reduction reaction, and the reagents they're going to use here is lithium aluminum hydride in dry ether. Alright? Now, Mr. William, tell me, right, reduction, is it the gain of hydrogen or the loss of hydrogen?
It's a gain of hydrogen.
And what about oxygen?
Oxygen is the loss of oxygen.
Okay, so I'm going to go to the carboxylic acid here. Now do this with me, guys. I'm going to remove this oxygen completely. And we're going to gain hydrogens. We're going to gain 2. So go to that carbon there, gain 1, gain 2. And you can see that. That is exactly how I form my primary alcohol. Okay, that's it. So this is a very simplified mechanism on how to reduce a carboxylic acid into a primary alcohol. And take note, this is important. You need to make sure the reagent that you use is a very strong reducing agent, lithium aluminum hydride in dry ether. Okay, this reducing agent is so strong. Do you need to heat it, Mr. William?
Nope, you don't need to heat it because it's very, very strong.
Yeah, RTP will work just fine. Okay, so you cannot use weaker reducing agents such as sodium borohydride or H2 in nickel. It will not work. All right, for carboxylic acids. Now, this mechanism here, it's a bit too complicated. We'll do this in class. Okay.
Alright, so Mr. Tim, we have gone through quite a fair bit about carboxylic acids. Well, that's actually just the start because there's another portion to it which is known as the acid derivatives. Right? So if you take a good look, how does carboxylic acid typically looks like? It will have a C double bond O together with OH. What is a derivative? Now, a derivative is where the OH has been replaced by something else, right? So usually it's replaced by someone with electron withdrawing property. So you can see over here, the OH has been replaced by an X, and X can fall into different categories. You know, X can be a halogen or chlorine, then we'll term this an acyl chloride. Now, X can be OR, which we'll call ester. X can be NH2, which is called amide. Now, the important thing is, one glance you're able to tell us what exactly do these functional groups belong to. For example, you can see COCl will be termed as an acyl chloride, COO with an R will be termed as an ester, and then your amide will be a CONH2. So it's crucial that you are aware what are derivatives of carboxylic acid.
Okay. Now, so we're going to talk nomenclature now for acyl chlorides. So like what Mr. William said, an acyl chloride is when we have the acyl functional group, and the acyl functional group, the carbon, is bonded to a chloride. Now, nomenclature is just this. It's quite simple. Instead of calling this, if this was OH, you would call this an ethanoic acid, right? Now, because it's Cl, you're just going to replace the suffix oic acid into OL chloride. So instead of ethanoic acid, we call this ethanoyl chloride. Now again, same thing. Instead of calling this benzoic acid, right, just go to the oic sound, so benzoyl chloride. That's it.
Well, Tim, there's only one way for us to prepare acyl chloride, right? And that's through carboxylic acid, which is a reaction I think we have just gone through not too long ago, right? So the key idea is your OH is going to be replaced by the various chlorines and their various reagents. Come remind them again, what is the cleanest reaction?
Now again, the cleanest reaction is when your byproducts are in a gaseous state. So that is the last one, SOCl2, SO2HCl. Both in gaseous, I do this reaction, the gases escape.
Yep.
So, Mr. William, we're going to talk about chemical properties of acyl chlorides now.
Okay.
I want you to focus on the carbon here and tell me, right, do you think acyl chlorides are nucleophiles or electrophiles?
Well, if you look at the carbon, you do notice that they have an oxygen and also a chlorine that's bonded next to it. And since oxygen and chlorine are both electronegative, they're going to draw electrons away from the carbon, and you expect your carbon to have a delta plus.
Yeah. So acyl chlorides, they are electrophiles, okay? Now let's compare with a carboxylic acid. Now Mr. William, tell me, right, between chlorine and an oxygen that we have here, who do you think is more electronegative?
Oxygen should be more electronegative.
Yeah, so if oxygen is more electronegative, now hear this out, I can tell myself that oxygen is going to suck electrons more away from the carbon, right? So the carbon in carboxylic acid becomes a bigger delta plus, it becomes a stronger electrophile. Now, is that correct, Mr. William?
It sounds like it, doesn't it?
Yeah.
Right? It sounds like if I have two oxygens, they're going to draw electrons more from my side, and therefore I should have a bigger delta plus.
Exactly.
Right? It sounds like that, but unfortunately it's not.
No, it is not. So sadly, life is not that simple, okay? So actually, acyl chlorides, they are super electrophiles, and in class, we'll discuss this with you again, all right? So highlight this for me first. Acyl chlorides, ridiculously strong electrophiles, okay? Now, being electrophiles, acyl chlorides, they actually undergo nucleophilic sub-reactions. Mr. Willem, can you go through this with us?
Yeah, of course. Now I need you to draw parallel relationship with whatever we have learned previously. Now when we did carboxylic acid, the whole idea was simply to replace the OH with an incoming nucleophile. So we expect similar reactions for acyl chloride. Now one of the key reactions that we have learned in nucleophilic substitution, we did learn it this way, where you have a nucleophile trying to attack the delta plus carbon and kick the leaving group away, and the end result is you have a nucleophile attached to the R, and the X minus will be the leaving group. So it is virtually identical. However, in this reaction, your substitution is occurring on the C double bond O, right? And that's why we call this a nucleophilic acyl substitution reaction. Now, if you look at the actual mechanism, what really happens is the nucleophile will come in, the double bond will break, electrons will shift up into a O minus before electrons shift back down to reform the CO double bond, and then you kick the leaving group away. Sounds pretty complex, doesn't it?
Very, oh my
Okay, so
gosh.
why not we do a simplified
Yeah,
version for
yeah.
them just to make things a lot easier, right? So the whole idea is technically you can see that the pi bond will first break and later it's going to reform. Now in reality, and H3 is like that, but then we are doing H2 or maybe H2.5, all right? So what's going to happen? We're going to simplify things for them, right? So how do we draw it? Everyone, I just need you to draw this with me. Draw an acyl chloride, and you have a nucleophile coming in to attack the delta plus carbon. Instead of breaking and reforming the pi bond, just break this straight away, right? Just kick the leaving group straight away, and the end result is you have the nucleophile attached, and then you have the Cl minus as the leaving group of the reaction. So you can see it kind of gets a job done because your chlorine has been replaced by a nucleophile. This is the simplified version.
Yep.
All right. Now we're going to bring this mechanism into the reactions of acyl chloride. So Mr. Tim, can you walk us through the process, how this thing works?
Yeah. So as usual, we say acyl chlorides, they're electrophilic, right guys? So one more time, nucleophile. Let's draw this here, okay? Expose the lone pair, you're going to attack the carbon. The simplified mechanism, break that CCl bond. Now in these three reactions here, 11.1, 11.3, 11.2, now take note, since acyl chlorides are super electrophiles, they are very, very reactive. All your conditions are very mild, RTP, RTP, okay, 11.2 as well, RTP, all right? Now, so let's talk about the nucleophiles in each reaction. Very quickly, just do this with me. Expose the lone pair, 11.1, on the water, okay? Tell yourself, the water molecule, that lone pair, nucleophilic, nucleophile, attack electrophile, break off that CCl bond, and that's how you get this carboxylic acid here. Same thing for 11.2. One more time, expose the lone pair on the oxygen, attack the carbon, break off that CCl bond, and you get this ester here. Last but not least, 11.3, once again, expose a lone pair on the nitrogen, nucleophile, attack electrophile, break off that CCl bond, and that is how you get your amide functional group. Okay? And that's it. So these are your reactions of acyl chlorides. The rest of the reactions we'll cover in class in greater detail. For now, this is good enough.
All right, see you guys.
Bye-bye.